Okay, after the difficulty that is 6-2, and actually when you look back on 6-2, it's not all that difficult. It's just, after you've only had one application of the integral to find area under or between curves, uh, the first time you deviate from that and start applying it to things like volume, it's a little uncomfortable. But once you've done it, once you've gotten the hang of it, looking back on it, it winds up being relatively easy. 6.5 by comparison is so easy. It's fantastic. I love it. Okay, so it's like at the end of chapter 6 where you've had a couple of daunting tasks, it's like that breather that you get. Okay? So let's just say that I have a constant function. Okay? And let's say that that area under the curve is equal to 15. And I say, okay, the area is 15. This is y equals what? Well, you pause for a second and you say, well, you haven't really given me much information. You haven't given me enough information. Because in order to find this, which is basically this measurement right here, okay, y equals, I need to know this measurement, which is b minus a, right? Okay, well, let's say that this is 2 and 5. Well, obviously, then the width right here of the interval is 3, and the height is 5, okay? Let's say that this is 2 to 7. Well, then the width of the interval is 5 and the height is 3, right? In order to go from area to height, I have to divide by the width. Now, the question then becomes, was that the same if it's not a constant function? Well, the only thing that's different is obviously there's no constant height because it curves. But what you do get when you divide by the width, you don't get a specific height, you get the average height. And if you get the average height for a function, you're really getting the average function value, the average output, okay? So that tells us that average value of f of x is the area under the curve from a to b divided by the width of the interval. It really is that easy. If this represents the area right here, here you're dividing by the width. And if you divide by the width, you're going to get the average height or the average function value. Okay? Well, let's do one or two examples. It really shouldn't take all that much time. Okay? Let's say that we have y is equal to x squared plus 2x minus, minus 6. And let's say that we want to evaluate it on -2 to 1. Well, let's go ahead and look at that function. Clear, 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 clear. So we have x squared, clear, y equals, we have x squared plus 2x minus 6. And let's go ahead and zoom 6 that bad boy. Now obviously from -2 to 1, all of the values are negative. So we're obviously going to get -2 to 1. We're obviously going to get a negative average value. if all of the values are negative. Now actually, let's change the window again. Let's get rid of the positive y values. Let's go to negative 10 to 0 so we can see a little bit more of the curve. Now that window that I've chosen is negative 2 to 1, the interval, and negative 10 to 0 on y. Okay, well let's go ahead and figure that out. Let's go ahead and find the area under the curve of x squared plus 2x minus 6 dx. And just for giggles, let's go ahead and do it by hand. And we're going to get 1/3 plus 1 minus 6 minus, and we're going to get negative 8/3 plus 4 plus 12. Okay. Well, this is 1/3 minus 5 plus, and let's go ahead and just distribute that, and we get 8/3 minus 16. Well, I did it this way because the 1/3 and the 8/3 combine to be 9/3, which is 3 minus 21, which is negative 18. Oh gosh, this is going to turn out nice and tidy for us. That is the area under the curve. So all of the area between this curve and the axis, if I were to shade that in, it would be negative 18. If I want to find the average function value, all I do is take b minus a of that same integral, okay, dx, and so I have 1/3 times negative 18 or negative 6. This is the average value. Well, let's go ahead and look at that and see whether that makes sense out of what we can actually see. If we actually have a function of y is equal to negative 6, does it look like the average value of the curve on that interval? And I would venture a guess to say yes. That curve, if you were to hammer it out into its average value, its average distance from the y-axis, from the x-axis, it would be that line right there. Okay? And that's kind of neat. Okay? So let's go ahead and do another one. This one, let's do one that actually requires, well, I don't know whether it requires a calculator. We'll use the calculator anyway. Let's say we have y is equal to x plus sine x, and we want the average function value from 0 to 2 pi over 3. That's obscure enough. That'll be helpful for us. Well, I know that my average function value, and I've never actually seen a very good abbreviation for that, but whatever, is 1 over b minus a, the integral from a to b, of f of x dx. Now in this case, of course, it's not f of x, it's y, but same thing, right? So we have 1 over 2 pi over 3 minus 0, from 0 to 2 pi over 3, x plus sine x dx. Now let's go ahead and actually do this by hand, since we haven't done one by hand in a little while. That's 3 over 2 pi, after I take away the 0, and obviously it's in the denominator, so it's the reciprocal of that. I'm going to get x squared over 2 minus cosine x from 0 to 2 pi over 3. Okay, well here we start to wonder whether it would probably be a good idea to use the calculator, and I think it would be. Let's go ahead and let's go 0 to let's go ahead and set the window first. 0 to 2 pi, and we'll go pi over 4 as the scale. 0 to 2 pi and pi over 4 as the scale. Actually, since we're actually going 2 pi over 3, let's actually go 2 pi divided by 3. And let's go pi divided by 6 as the scale. I think that would be a little bit better. Pi divided by 6 as the scale. Okay, well, let's go to y equals. Let's plug in x plus sine x, and let's graph it. So on 0 to 2 pi over 3, that is what our function looks like. Okay, well, let's go ahead and go back. Let's go ahead and let's integrate and find the area under the curve. Actually, let's just go ahead and just find the average value. So we already have simplified it. So it's that times the integral from 0, and I love the fact that you can actually use the fractional notation inside the limits of integration. That makes me very happy. Of y1 dx. And that ought to give you the average value. Well, let's go ahead and see, because obviously without that coefficient, that integral would be the area under the curve. By multiplying by 3 over 2 pi, you're dividing by the width of the interval. Let's go ahead and see. Let's go ahead and store that into A, okay? And let's go over here and let's actually see what it looks like when we graph y is equal to A. Now, does that red line look like it is the average value of the function? And the answer is yes, okay? Now, the only other thing it really, you know how to integrate. All you have to do is divide by the width of the interval to find the average value. Now, we've talked about averages before. Back when we did derivatives, we talked about the average slope on an interval. And when we did that, we had this little thing called the mean value theorem. The mean value theorem for derivatives, the original mean value theorem, said what? Well, it said average slope on an interval will be equal to the instantaneous slope at some point on the interval. So, in terms of notation, that was f of b minus f of a over b minus a is equal to f prime of c, and of course, for some c value in a, b, right? And that was the mean value theorem, as was stated, I think, in chapter 3, okay? Well, the mean value theorem for integrals is basically the same logic. It's just a different average. If the average slope on an interval has to be equal to the instantaneous slope at some point within the interval, then it makes sense that the average function value needs to be equal to some actual function value within the interval. And we saw that on both graphs, right? We see that on this graph, which we actually still have on the screen. It's that point right there, the point where they intersect. That point is the point at which the average slope, the red line, is equal to the instantaneous or a particular output value for the function, meaning the blue graph, okay? And so just like the mean value theorem, you can actually find that point. So let's go back to the first example, okay? The first example that we did happened to be y is equal to x squared plus 2x minus 6 on negative 2 to 1. I remember that the average function value wound up being negative 6. Okay, well, negative 6, you basically take the average function value and set it equal to the variable expression for any function value, and you just solve, right? Those two cancel out. You get x times x plus 2 is equal to 0. And so that function is equal to -6, either at 0 or at -2. And of course, you're looking for it on the open interval. So the only place where it happens on the open interval is x is equal to 0. It really is that easy, guys, okay? So just like in the mean value theorem where you took the average slope and set it equal to the variable expression f prime of c and solved, here too you find the average function value and set it equal to the variable expression for any function value, get your answer or answers, evaluate it with respect to the original interval, and state your claim. Okay? I don't think we really have to go over this too much more. So I will post this video, and I will go ahead and wait for you to ask if you need more clarification before I unnecessarily toil away at further videos, which just wind up being redundant and unwatched. Okay? I don't think you're going to need any more beyond this. It's a pretty straightforward concept. Please do, as always, email me if you have any problems, any questions, any struggles, any requests, and I will try to attend to those just as fast as I possibly can. Bye, guys.